We will just start at 6:05. Maybe someone will join. Today, most of the questions will be related to BJT again. All questions are simple as we did in last session. So, without any more in-depth details, we will just solve these questions and move to the MOSFET at last. Just few more minutes and we can start. Okay, so let's just go to first question. What does it say? Just a moment. Okay, so the question is on calculation of small signal voltage gain. We have all the details given to us for this particular BJT. First, from the symbol, what does symbol say? Is it an NPN transistor or PNP transistor? Sorry, this is for this kind of symbol we draw for MOSFETs. So symbol is in this form, and if it is in this form, so as I said in the first session or second session, if you want to just remember PNP and NPN, so how you can remember is it? Remember it as a PN junction. Current flows from P to N, right? So arrow will be from P to N. So here arrow is from this direction to this direction. So this has to be P, this has to be N. Similarly here, this has to be N. Oh, sorry, this has to be P, this has to be N. So this is a PNP transistor. What does that mean? This is a PNP. So emitter base should be forward bias. This is emitter, this is collector, this is base, right? So all the values for these or for resistors is given to us as 470 kilo to kilo beta that is IC by IB is given to us as 80 VEB on. Why not VBE? Because this is a PNP transistor. So you have to just change from VBE to VEB. Here VEB will be positive, and in NPN transistor VEB will be negative, right? So just to check, you put correct values. You have to be careful about the sign of the values. Okay. So this has been given to us as plus minus 0.6 volt. Okay. This is for saturation condition and thermal voltage and early voltage. Early voltage is, you know now what is early voltage, right? Early voltage is given to us as 120. So what do I have to find? Find the magnitude of small signal voltage gain. And in dB, assume the signal coupling capacitors are shorted while doing the small signal analysis. First, let us just understand why we use this capacitor here. Why? The question is why we use. Hello. Okay. Hello, Krishna. So have you done this? Have you attended last session, yesterday's session? Hello, can speak. Okay, just say here. So I was just saying that why we use this capacitor. This capacitor. What is the purpose of this capacitor? If I have AC signal plus DC signal, we know capacitor blocks DC, right? And passes AC, right? So if I have transistor, I apply some DC voltage here and I apply some AC voltage here. I don't want this AC, if this is a resistor here, if this is a resistor here, and I add this capacitor here. So I don't want my AC signal, sorry, or DC signal to come and go in this direction. This DC is only for biasing purpose. I don't want my DC signal to flow in this path, and similarly we use actually inductor here. One moment. It's not just a simple resistor. It is we use an inductor here and we use capacitor here. And we don't want our AC signal to go in this direction. We want our whole AC signal to pass in this direction and DC signal to pass in this direction. So for that purpose, what we do is that we use a LC circuit, right, such that this blocks DC and this blocks AC, right? So that is the purpose of capacitor here, such that the DC signal only gives a voltage here and does not pass through this path. So there is a DC current will be 0. That is one thing. Now we have to find small signal voltage gain. Small signal voltage gain. What does that mean? Gain is, this is a voltage gain, right? So that will be V output by V input. But here we are talking about AC signal, right? So what we do is that we first bias our transistor. TX is the short form for transistor. We first bias the transistor, then apply AC for it and find the characteristics such as gain, right? So let's just see the circuit. Now to find small signal voltage gain, what we do is that we make an equivalent circuit. We make an equivalent circuit. Okay, so what we do in equivalent circuit? DC to ground, right? On this notation, or can use this notation. DC supplies will go to ground and AC will remain as it is, and we short capacitors. If it's not given capacitor is still blocking the voltage or is not perfectly short, you can use the approximation of shorting the capacitor for AC signal. You assume that frequency is high enough to short the capacitor. So circuit will become, I have input I have resistor here, I have R pi, this is Vs, this will be Vs, Gm, this is ground, Gm Vs. And since early voltage is given, so we have to take into consideration the output intrinsic resistance. We should not ignore that. We have here RC and we have R0, right? And this is V out, right? Don't worry about the notations, what is the direction of current. End of the day, you will be able to find the direction of the current from the symbol. Here it is an emitter, the current will be flowing from emitter to collector only. So this has to be actually in opposite direction, but that won't matter because we will just find the magnitude of the gain. Okay, so this is our equivalent circuit. And this is my biasing resistor RB. Okay, now to find gain, what we do? We will look at our output part, right? And apply KCL here. So I'm not writing directly formula. I know the formula, but I'm not directly writing it because I want to see how we can reach that formula. Okay. So let's find a KCL at this point. What we'll get? We'll get V output by R naught plus, we assume the current flows in this direction, right? V output by RC plus, here the current flows, GM Vs equivalent to 0. Okay, what next? V output will be equivalent to R naught RC. This is R naught plus RC equal to minus times GM Vs, right? So magnitude of V naught by Vs will be equivalent to GM times RC. One moment. RC R naught divided by RC plus R naught, right? So this is the formula for small signal voltage gain. Okay, now if We have to find magnitude in dB. What we do for voltage, for power. What is the formula? Okay, let's write the formula at your end. Formula says for if you have voltage variables that in dB, if you want to denote it in dB, you have to use this formula. Let's say here V dot by Vs. Okay, and if you have these V naught and Vs, if they are in power, then you have to use 10 log V naught by Vs. To remove any confusion, what I will do is I will write P naught by Ps, where P naught and P are powers. Okay, just to make you understand the difference, this is because power is directly proportional to voltage square. So if you do here, replace it with voltage square, 2 will go outside log, it will become again 20. So this is the formula to have the values output volt gain in, sorry, not output gain, gain in dBs. Now for this question we have to calculate this gain. So for that, what do we need? What do we need? We need GM, we need R naught, right? Let's go back and see. Let's calculate these values. What is GM? GM, we have derived it in last session. GM can be simply calculated as IC by VT, right? And beta is given to us, right? 80. So we can directly write it as beta times IB by VT. Okay. Now, if the current IB flows in this direction, so since there is zero DC current in this path, so this IB has to flow in this direction, right? So for IB, we can directly write it's equivalent to VB. VB is voltage at this point marked by X divided by RB, right? This is the only path from which the IB can flow in the circuit. So IB has to be equal to VB by RB. Now, if you again look at the circuit and the given data, we have VEB equal to 0.6 volt, right? So from the potential difference function definition, VEB can be written as VE minus VB, right? And this is equal to 0.6 volt. Now we have to find VB. So VB will be equal to VE plus 0.6 volt. Alright. Yes. So VE is given to us as 10 volt. Wait, I think I did one mistake here. Yes, sorry. This has to be this has to be minus here. Okay, so this is actually VE minus VB is VEB, so I will take VB on this side and VEB on this side. So this is VE minus 0.6, that is 0.6 volt, 10 volt, that will be 9.4 volt. So VB is 9.4 volt. Now you can replace it in this formula. So we'll get 9.4 divided by RB. We look for RB. RB is given to us as 470 kilo ohm, right? Now let's just calculate it. 9.4 divided by 470. That comes out to be around 1 by 50. That is 0.02 milliampere, and that will be equal to 20 microampere, right? So then, now we have IB in our hand. We can directly calculate GM, right? That will be 80 multiplied by this 20 microampere divided by VT. VT is given to us again as 26 millivolt. Now if we just calculate it, you will get GM of around 80 multiplied by 20 divided by 26. It comes out to be around 61.53 milli. Let's verify. 60 divided by 260. That comes out to be around 61 milli. We can write it as 61, around 61 milli. Okay, so this is the value for GM. Now we have GM. What else we need? GM we got, that is 61 milli. Now we need R0. Again, let's go to this R0. What is given to us is again early voltage. So let me just write it here. GM we got as 61 milli. What is the definition of R0? R0 is simply VA by IC. So that will be VA by beta times IB, right? So R0 will be equivalent to VA is 120 volt divided by beta 80 into 20 microampere. Calculated, you will get an R0 of around 75 K. So now you have GM, you have R0. RC is also given to us 2 kilo ohm. Okay, so this is 61 milli into 2 kilo ohm into 75 kilo ohm divided by 75 kilo ohm plus 2 kilo ohm. Okay, the 1k will go, so you will find a gain of, calculated, you will find a gain of around 120. Okay, so now I have given you the formula to calculate it in dB. So in dB it will be given as 20 log of 120. That is comes out to be 40. That comes out to be 41.58. Okay, so what we did in this question is we understood why we use capacitor here, and we had to find then small signal voltage gain. We know the definition of small signal voltage gain. We understood how to draw equivalent circuit for BJT, and also we understood how to calculate the values in dBs, right? Okay, so just remember that we have to use these values in other questions as well. Let's go to part 2. Okay, so what does this question say? Find the small signal input resistance and output resistance for the circuit shown in figure 4.1. Let me just clear a few things. Okay, let it be. So this is our circuit. Let me just draw it. Okay. For small signal case, this will go to ground. So what would we have to find is, we have to find small signal input resistance and small signal output resistance. So let us just draw. This will be Vs, this is Rb, this will be R pi. One thing I think I have written R pi here. This will be again Gm Vs, this will be Rc, and this will be R naught, right? So how do you find input resistance? If we have to find input resistance, if there is any supply here, you ground it, right? Then we use test source at input for calculating input resistance. So what will we do here? Since it is grounded here, so we can ignore this part. Let's just focus on this part and ignore this part as well, the supply as well. Just write these nodes. This is my resistance, this is R pi. So what we have to do is, we have to attach a supply voltage here, Vx, Ix. Let Vx and Ix be the test voltage and test current. What will happen is that Ix will flow in this branch. This is a parallel combination, Rb parallel R pi. So my resistance will be calculated using Ohm's law again, right? I have to find just this equation, Vx is equal to Ixr, and my R is here input resistance. So here what we will get input resistance as, Vx will be equivalent to Ix Rb parallel R pi. So my input resistance is equal to parallel combination of Rb and R pi. Now if we go back to question, Rb is given to us at 470 kilo ohm. So what people may do wrong here is, if they ignore this resistance, sometimes while drawing the equivalent circuit, you can do this mistake and you just draw Rb here and ignore R pi. But what will happen is that you will, if let's say this is an objective oriented paper, you will just ignore these three options, right? Because Rb is 470k, then you will look for the answer in these two parts, and maybe you will guess and you will do wrong. But this has to be very careful, You have to be very careful while drawing the equivalent circuit. R pi should not be ignored. That is an important element in equivalent circuit or for BJTs. So how do we calculate R pi? R pi, you know, is beta by given by beta by GM, right? We have calculated GM in previous part. Beta is given to us. Now can we write directly what R pi is? 80 by 61 milli, right? GM was 61 milli, right? Yes. So let's beta is given to us as 80. That comes out to be 1.312K. This is my R pi. Now look here. RB is 470K and R pi is 1.312K. And these are in parallel combination. So my R input will be equivalent to 470K multiplied by 1.3K. Let's assume it 1.3K. 170K plus 1.3K. Let's just solve this. 470 comes out to be around 1.3, oh sorry, 1.3K. So look here. Here R pi was less than RB, biasing resistance. So this would have been a very severe mistake if we had ignored this. Now if for example my R pi is very large than RB biasing resistor, then at that time if we ignore this RB because these are in parallel combination, we get always a smaller one. Then there is a provision if we ignore this. Okay, so now we got the input resistance. Now what is the next step? Output resistance. We again use test source at output. Short or ground. Voltage sources. On the input side. Open if there are any current source. This in this for not just for output resistance, for any case. This is the way. I will draw just output part. As I said, we can ignore this part since it's ground. We can ignore this part to calculate input resistance. Similarly, we can ignore this part to calculate the output resistance. And remember that since we are calculating the output resistance and we ground the input signal, my Vs will be equivalent to 0. And my Vs is equivalent to 0, my Gm times Vs will be equivalent to 0 as well. So what I am left with is, so I have to open this. So what I am left with is RC, and here is my test source Vx, and current flows is Ix. So my Vx will be equivalent to, this is open because my input signal is 0, the transistor is off. So Vx is Ix Rc. Therefore Vx by Ix is equal to Rc, which is my output resistance. Now Rc is given to us in a equivalent to 2 kilo ohm, and what that is our output, and our input we calculated as 1.3 kilo ohm. Let's just look at the options now. Now you can see here, which one is the correct option? D part, right? So this is how you will find input and output resistance. Okay. Okay. Now next. What is the next question? Find the value of signal coupling capacitor C1 such that lower cutoff frequency of amplifier is 200 radian per second. Radian per second is the unit of omega, and hertz is the unit of frequency. Yeah. So omega is given to us. Now we have to find value of C1 such that after that frequency the capacitor may behave as a start behaving as a short. Just drawing, this is the equivalent circuit, drawing an equivalent circuit for the figure 4.1. You can look at it. I have one in front of my screen. So this is my R pi, this is RB, this is C1. Okay, one thing that I did, I think, wrong in previous part is that there should be R not here as well. So my output resistance is not just RC, it is just correct. This is RC parallel R0, RC parallel R0, and my RC is 2 kilo ohm, so output will be equivalent to RC R0 divided by RC plus R0. Have I calculated R0? Yes, I think that is 75k. So my R output will be equivalent to 2k into 75k divided by 75k plus 2k. 150k square divided by 77k. 1k will go. That will be 150 divided by 77. That is 1.948k. So that won't change, I think, the option which is correct, but this is the correct value. We forgot R not. Okay. So now in this question, what is the purpose? We have to find the value of C1. So how do we do that? What people just directly write is you have C1, then you look at the input resistance here. You know the input resistance we calculated in previous part, that comes out to be 1.3 kilo ohm, right? So what they do is write omega R in C1 equivalent to 1, and you find C1 as 1 by omega R in, right? So why does this formula come from? How do you obtain this formula? If I just put in values in this formula, you will get your answer. That is fine enough. 200 into 1.3k. So let me just still calculate it using this formula. Then we will see how we can obtain this. Okay, that comes out to be around 0.00384 milli, that will be 3.84 microfarad, right? This is option number A. But let's see how we obtain this formula. We have our equivalent circuit here, right? Now what we have to do is let's find gain. What is the gain of the circuit? This is one fine thing. This is there is no issue with this. Let's just see how we can obtain this equation. So how will we find gain? We use KCL over here. RC is parallel to R0, so let's write V output divided by RC parallel R0 plus GM VBE equivalent to 0, right? We will get V0 as minus GM RC parallel R0 VBE. So now if we have to find gain, we have to find VB in terms of V source voltage or VAC signal, that is V in, given us here as Vs. So now can you find what is VBE? Simple voltage divider. What are the two parts? One is the parallel combination of RB and R pi, right? And next is C1. C1 will give a reactance of XC1. Let's denote it to XC1. So now you divide the voltage between XC1 and parallel combination of RB and R pi. So what you will get? VBE will be equivalent to RB parallel R pi divided by RB parallel R pi plus XC1 multiplied by Vs, right? So now I substitute this value in here. We get V output is equivalent to GM RC parallel R0 and replace it with RB parallel R pi divided by RB parallel R pi plus XC1 Vs. So my gain, that is mod of V0 by Vs, will be simply equal to GM RC parallel R0, that is one term, and RB parallel R pi divided by RB parallel R pi plus XC1. What is XC1? Simply 1 by j omega C1, right? 1 by j omega C1. Now what do we do here? You remember poles? This is one pole. If I have gain versus frequency plot, gain goes like this, right? So when it strikes one pole, here the first pole will be at frequency of omega 1. Let's say this is one pole, that will be, we will calculate that, and the gain starts dropping, right? So this is our first frequency, first cutoff frequency. So that will be given by this formula. When 1 by mod of j omega c1 will be equivalent to RB parallel R pi. This is how 1 by j, that will be 1. This will give me omega c1 as 1 by RB parallel R pi. And what we had to find was C1. So C1 will be simply equal to 1 by omega RB parallel R pi. Now if you go back here, what was input? What was input here? Input resistance formula. Mm, here input was given by RB parallel R pi, and value is 1.3k. That is same as the one we directly used form line. So this will give you the answer of how many farads order? 3.85. So this is how you achieve this formula, right? Okay, let's move on. Okay, this question is also based on the circuit. Um, 1 second. Mhm. Okay. Okay. So what we have to sorry, what we have to find is what is happening. We have to find output signal maximum such that it is without any distortion. What do you mean by distortion? Anyone? What is signal distortion? If I have this as my input, if I have this as my input, this is my amplitude, right? So if I pass it through a black box, which is my transistor, what will I get? Amplified signal. If it is operated in linear region, right? I will get amplitude of A dash, which is higher than the input signal. So what do you call this signal as? Undistorted signal, right? There is no distortion in this case. So but if I get an output signal, if I get an output signal such that there is this behavior, this is called as a distorted signal. So that's why it is given as find the maximum output signal swing without significant distortion. So in this question we have to find how far peak to peak we can go such that my output signal is not distorted. So if I apply a perfect sinusoid, it should give me perfect sinusoid, right? So what we will do is first we have to find biasing condition of transistor, right? Because it is a biasing condition is DC condition and over which we apply our input signal, right? Let's just find first V output. Let me just draw here circuit. Let me just draw here. and this is my output, right? Okay, now I have to first find, since we have to find the maximum swing in output voltage, we have to find first V output, that is DC. And what is V output equivalent to? The current of IC flows you, right? It will be IC into RC, right? RC is given to us. Is IC given to us? No. But we calculated, I think we calculated IB, right? So we can write beta times IB RC as V output. Let's find what was IB equivalent to. Not here. Okay. Okay, IB is 20 microampere. My IB is 20 microampere. So my V output will be equivalent to beta is 80, 20 microampere to RC. RC is 2 kilo ohm. So my V output will be equivalent to V output will come out to be, sorry, 3.2 volt. So this is my DC condition for the transistor, and your, this is irritating. Now we got the DC condition. We know supplied voltage is equivalent to 10 volt, right? Supply voltage, that is here VE equal to 10 volt. Also in question it is given that VEC saturation is given as equivalent to 0.2 volt. Okay, VEC is given to us 0.2 volt. So now what does that mean? If I go on increasing this V output, VEC, this is E node, right? And this is C node. Let's say for DC condition, at DC, at DC, V output is equivalent to 3.2 volt. What is my VEC equal to? Apply KVL in this loop. We will find it as 10 volt minus VEC minus V output, that is 3.2 volt, equal to 0. That will give me VEC equivalent to 6.8 volt, right? This is initially what my VEC is equivalent to. And what is my provision? What is my provision here? So I can go from VEC set till saturation of 0.2 volt, right? So my VC can increase, right, due to input signal, but it should be restricted up to the point where VEC is equivalent to 0.2 volt, right? So we can treat it as if our applied voltage is at a reference of 10 minus 0.2 volt, which is equal to 9.8 volt, right? So we cannot go above this voltage such that my VEC goes below 0.2 volt, right? Okay, so now you have this 3.2 volt as a reference. You can go maximum of 9.8 volt, right? So if you have an input signal which can go a max of 6.6 volt, but now if you have this peak voltage of 6.6 volt, and since it is at 3.2 volt, it can drive a transistor to cutoff stage, and what will happen is you will have a distorted signal at input, right? So we don't want that, right? So my bottom side negative cycle, in negative cycle, my peak to peak voltage should be restricted to 3.2 volt. So ultimately during the positive cycle or during the negative cycle, the input signal will not get distorted. So this should be 3.2 volt only. This should be 3.2 volt only. So my peak to peak voltage, that is this voltage, is 3.2 plus 3.2 or 2 times peak voltage, which comes out to be equivalent to 6.4 volt. So this is the answer for this question without any signal distortion. The maximum you can go is 6.4 peak to peak. Okay. What next? The question says find the maximum input signal swing for the circuit. Okay, now in previous question what we are supposed to do is to find maximum output signal swing. Right? Now we have to find maximum input signal swing. Well, this is a direct this can be calculated directly now that you have output, max output signal swing is known to you, that is 6.4 peak to peak, right? So you know V output is gain times V input, right? So your swing ultimately will be given by the same formula, because that is also the output voltage and input voltage. So my V input swing will be simply equal to V output, what is its maximum swing, by gain. This is 6.4 peak to peak, that is known to us. What is the gain? Gain we calculated earlier various times. That will be given by simply equivalent to GM times RC parallel R0, right? And this is GM we calculated as 61 milli, and RC is 2K, multiply 75K divided by 75K. R0 is 75K, right? Let's just confirm. Yes, R0 is 75K. Hmm. 2K. Just use the calculator, you will get a gain of, okay, let's just write directly swing. Now your input swing will be equivalent to 6.4 divided by gain. It will be 77k divided by 61 milli into 2k into 75k. Use the formula, use these values, you will get the input swing of 52 milli peak to peak. This option. So this was all for question number 1. What we did in this question is, let's just summarize. We had the circuit, right? Everything was given to us. We again repeated how we can understand what is the direction of by arrow symbols, what is the type of transistor, what is the type of BJT we have. And then we found how to find small signal voltage gain. Then we also studied what is the purpose of using capacitor here. Okay, then small signal equivalent circuit, how to draw that and how to find out gain from the circuit. How to use repetition of KCL was provided also. This is the formula, how to calculate your values, how to convert them into dBs. This is how you do it. Then again, how we can use test sources at input and output to find the input and output resistances. These are the steps that you should do if you apply any test source at output. 1 second. Then what you have to do is you have to short the voltage at input and open the voltage at open the currents. Okay. Then what next? Okay. Then we also found that how we can approach to this formula, how we can achieve this formula. Okay. And then this is how you obtain it. Just for the part of practice, you can use multiple capacitors here. Then you can derive at your home also. Okay. This is for single capacitor, right? If you have multiple capacitors, you can have multiple poles and their relative cutoff frequencies will be different. Then we also studied about the signal distortion and how you can achieve a signal within the limited maximum swing such that the signal is not distorted at the output. And then you have also how you can, if you have output signal, output voltage swings, how you can find the output voltage swings. Okay, let's move on. 1 second. This question number 2, again on BJTs. So what does the question say? You have circuit in front of you, you have all the values. So first question says find the DC voltage between emitter and collector terminals. Okay, so this is PNP, so this is E, this is C. We have to find VEC, right? Okay, fine. Let me write few values which are given to us. VCC is at 12 volt, right? VEB is at 0.7 volt. This voltage is 0.7 volt. Since R1 and R2 are given to us, right? And also we can find VE2. So what we will do is we'll first find VE, then we will find VC, which will give us a VEC equivalent to VE minus VC. So first goal is to find VE, right? Since VEB is given to us, we can write it as VE minus VB, right? One second. VE minus VB, and thus VE will be equal to VB plus VEB. Now can you find VB? R1 and R2 is given to us. It will be simply use the voltage divider, R2 divided by R1 plus R2 into VCC plus 0.7 volt. These all values are given to us. Let's just calculate VE. R2 is given to us as 80k, R1 is 40k. So my VE voltage will be equivalent to 80k divided by 80k plus 40k into 12 plus 0.7, right? That will be 80k divided by 120k, 12 plus 0.7, 12 10, k will go, this will be 8.7 volt. So now we have VE in hand. Now what we can do, one second. Now we got VE. Okay, now we need to find VC. But using VE, what we can do? You have E here, VCC here, you have E here. Can you find the current flowing through this resistor? And what will be that current? IE, right? Here it is IC. So current IE will be given as VCC minus VE by RE, and VCC is given to us as 12 volt minus 8.7 volt divided by RE. RE is given to us as 3.3k. Clear enough? This will be equivalent to 3.3 volt by 3.3k. This will go, IE will be 1 milliampere. Okay, now I have IE in hand. My IE is equal to IC plus IB, right? So my IE will be equal to IC plus IC by beta. Okay, this will lead to IC times beta plus 1 by beta is equal to IE, which will give me IC as beta times IE by beta plus 1. Now beta is given to us, right? Beta is given to us as 100. So my IC will be equal to 100 divided by 101. I is 1 milliamp, and this will come out to be, let's just keep it at this way. Now what we have to find from IC is VC, right? VC will be simply equal to IC RC. Now VC is equivalent to IC RC, that is 100 by 101 10 raised to power minus 3 into RC second. My RC is equal to 3.3 K. Okay. So it comes out to be 3.26 volt. Now VC is known to us, so we can easily find VEC, that is VE minus VC, that will be 8.7 volt minus 3.26 volt. Calculate it and we'll get an answer of 5.44 volt, right? Okay. Now, what does the next question say? One second. So next question says, if you now change your beta to 300, what will happen? Your VE B is same 0.7 volt. Your VE values will be same and VE will stand at 8.7 volt. Now what we have to find is, what is the DC voltage across the emitter, and we have to find again VEC. We again have to find VEC. So for that we have VE minus VC. VE is fixed at 8.7 volts. Now we have to find VC, right? So VC will be equivalent to IC times RC. Now let's see what IC is. IE is equivalent to IC times IC plus IB. Again, using this formula, we get IC is equivalent to beta divided by beta plus 1 IE. Here beta is 300, we will get 300 divided by 301 times IE. IE is 1 milliampere. So my IC, let's just calculate it, we get 300 divided by 301.996 milliampere. This is my IC, right? And then what is VC? 996 milli into 3.3 K. Solve it, we'll get a VC of 5.41 volt. This part. Okay. Next is find the ratio of small signal voltage gains of amplifier with and without bypass capacitor. Okay, so we have to draw equivalent circuit first. Let me just draw it. With all the capacitors, all the elements intact, can draw R1 parallel R2. This is that, right? Okay, this is your emitter resistor. GM. This is VB, this is VE, this is VBE, and you have your RC. Early voltage is assumed very high, so you don't need to write R0 because R0 is VA by IC. So when it is high, it will simply act as open circuit. So this is this, and you have one capacitor here, CE. This is C1. This is C2. Okay. So now what does the question say? Find the ratio of small signal voltage gains of amplifier with and without bypass capacitor. Here, emitter is the bypass capacitor. So we need to find gain when RE is not, RE is equal to 0 because capacitance will act as a short. So RE is shorted, not 0, it is shorted. And we have to find gain when RE is not shorted. Okay, that is CE is not present. Also, this is our equivalent circuit. Let's find first gain when capacitance is shorted. In that case, assuming input capacitance, output capacitance are also shorted. In that case, you have Vs here. That Vs will be here also. This is ground. This is GMVS. This is RC. This is V output. In that case, your V output will be simply equal to GM RC Vs, and your gain will be equal to GM RC. Have we calculated GM for this question? No. Okay. Now RC is given us. Let's see what GM is. Okay. GM will be given by IC by VT. Just find GM here. Okay. GM is given by IC by VT. You have VT given to us as 26 millivolt. I think we found IC in one slide. Okay, IC is here. It's around 0.99 milliamp. Okay, so at this condition, you can directly find GM as 0.99 divided by 26 millivolt. It comes out to be 38. I think something mistake here. Okay, this is milli. So this comes out to be 0.038. Now into gain will be to RC. Given us as 3.3K. That is 38 into 125. Okay, so this is your gain when there is no bypass capacitor. Now with, sorry, when there is a bypass capacitor, it takes a short. Now without bypass capacitor, how will my circuit look like? You have Vs, you have biasing resistor, you have R pi, you have Re, you have Gm. This is your Vs, this is your, let's say this is Vb, this is Ve, Gm Vbe. This is, sorry, this should not be connected here. This is my V output, right? So now you have Re as well. So what we can do here is that we have to find gain, right? Your VB, wait a second, okay. RB is R1 parallel R2. Just 1 second. Let me just check it. Mhm. Okay. Let's just apply KCL at this node. You will get V output by RC plus GMVBE is equivalent to 0. My V output will be simply equal to GMRC VBE, right? But here my VBE is, here my VBE is VB, that is Vs minus VE. And if I apply KCL at node VE, node E, what I will get? So this is the base current, this is emitter current, right? So I will get GM VBE plus IB is equal to IE, right? Okay. What I'm looking for is, okay, yes. So you, this VEIE, you can write it as VE by RE, right? So what will happen is, VE by RE is equivalent to GM times VB minus GM times VE, and your IB is again equal to VB by R pi minus VE by R pi, right? So you transpose this here, you will get VE is equal, and this also V equal to 1 by RE plus 1 by R pi plus GM is equivalent to VB GM plus 1 by R pi. VB, as I said, is equal to VS, then you can get VE is equivalent to GM plus 1 by R pi divided by 1 by RE plus GM plus 1 by R pi, and is equal to GM is IC by VT. IC by VT and IC you have calculated already, that is known. So now that you have VA in terms of VS, right? Now VE is in terms of VS. Now can you find V output? V output is GM-RC VBE, that is VB minus VE. That will be give me GM times RC. VB is VS minus VE. VE have, let's write it as lambda times VS. Lambda is GM plus 1 by R pi divided by 1 by RE plus GM plus 1 by R pi. Okay, so I can write it as lambda times Vs. My V output will be simply equal to GM times RC Vs 1 minus lambda. Therefore my gain without bypass cap will be simply equal to GM times RC to 1 minus lambda. And here lambda is given to us. Here what GM is known to us. R pi will be given by, what is the formula for R pi? Beta by GM. Please do check it, is it correct or not. And these values will be known to you now. Now you can find lambda, then you can find gain. Then what you have to do is that you have to just, if this is gain 2 and previous one is gain 1, you have to find gain 1 by gain 2. This is now only based on calculations. Alright. Now next question, it's again what we discussed earlier, how to find input resistance and output resistance. Again, let's just draw first equivalent circuit. For the case here, it is saying that the bypass capacitor is not present. So it's a the second circuit which we drew. So it will be Vs. It will be R1 parallel R2. It will be R pi Re Okay, what we have to find is input resistance. That means I have to apply a test source here, Vx, and current Ix flows such that Vx by Ix, when I do Vx by Ix, I get input resistance. Okay, let's just do this part. So here, what is the current that flows through in this branch? IB, right? And this is my emitter. What is the current that flows in this branch? IE, right? So I know IE is equivalent to IC plus IB. Just remember this, we may use it. Now if I have to find Vx by Ix, what will happen is the component of Ix will flow in this direction, component will flow in this direction. This is my IB. First let's apply KVL in this loop. What is voltage here? It will be given as IB. One second. VB can be written as now Vx. So Vx will be equal to IB times R pi plus IE times RE. So this is a KVL following this loop, and I can write it as IB times R pi plus IC plus IB times RE. Okay, using the formula I can write it as IC can be written in form of IB. Since our dealing has to be with IB, so what we'll do, we change every current in terms of IB. If I had to find output resistance, so I will change every component in IC, right? So my IC is beta times IB, so it will become beta times IB RE, right? So my Vx will be equal to IB times R pi plus beta plus 1 RE, just from the same formula, right? Just IB, I took IB as common. Now we have Vx in terms of IB, but we need Vx in terms of Ix. Looking back at the circuit, can we say that if I have current source I, this is I of R1, this is R2, what can I do? What is the amount of current that flows here? Here. We use simple resistor divider rule on currents, right? So I2 will be equivalent to R1 divided by R1 plus R2 into I. Same, we will do the same here. So my IB will be equivalent to current in the other resistor, that is R1 parallel R2 divided by R1 plus R2 plus R pi into Ix. So my Vx will be equivalent to R pi plus beta plus 1 Re divided by, okay, just let me multiply here. R1 parallel R2 so my input resistance, that will be given by Vx by Ix, be simply given by parallel combination of R1 R2 R. Okay, there should be, no, sorry, mistake here. I wrote it right? So this is R1 parallel R2 divided by R1 parallel R2 plus R pi multiplied by R pi plus beta plus 1 Re multiplied nothing. Okay, this is my input resistance. right? So let's just find few values. Let's first see what R pi is. R pi is equivalent to beta by gm, right? I'm a little bit confused about the R pi formula. Let me just check what is the formula for R pi. Give me a second. R pi is beta by gm, it's correct. And gm is IC by Vt. So let's just find beta is given to us, and this is question number. This beta is given to us as 100. Okay, and gm is your IC by Vt. Let's assume IC is 1 milliampere because we found out that IC is 1. Let's assume it's same. That will be 1 by 26 around. Okay, one. Let's write beta as 100 into 26. That will be give me 2.6k. So my R pi is 2.6k. GM is 1 by 26. So my R input R1 is given to me as 40k. 40k parallel R2. Okay. There is one mistake here. Sorry. So actually, mistake here is this should not be R pi. The two resistors go to previous slide. Here the two resistors are now, this is R pi in combination with Re, and the total resistance now is R pi plus beta plus 1. This should be R pi plus beta plus 1 Re. Okay, it should be R pi plus beta plus 1 Re here too. Should be R pi plus beta plus 1 Re. Let's just first calculate what is R pi. This calculated resistance, that is R pi plus beta plus 1 Re. That will be given by R pi. R pi was 2.6k. 2.6k plus beta is 100, that will be 101 into Re. Re is given to us as 3.3k. Okay, 3.3 plus 2.6, that is 5.9k. Okay, wait a second. Mistake. Plus 2. This is equivalent to 335k. This is R dash. Okay. Now it's in parallel combination with uh, R1 parallel R2. Now R1 parallel R2 is equal to 40k multiply 80k divided by 120k. That will be 80k by 3. Okay, now these two are in parallel. So our total will be equivalent to 80k by 3 into 335k divided by 80k by 3 plus 335k. That will give me 80 by 3 plus 61. That will give me 80 into 355k divided by 361k. 3k and k will go. Hello. Okay, so calculated, we will get 335 divided by around 24.75k. Okay, this is your our total. Okay, this is equivalent to your input 24. So this should be your correct option. So let's just see we did everything right or not. So what we first did was we find out what is the current flowing in this branch, because there is a no bypass capacitor, so we had to take a nodal potential V into also consideration. So this is not just simple resistance of R pi here, so the total resistance that comes up is R pi plus beta times beta plus 1 times Re. Now this becomes your total resistance from this point to this point, and it is in parallel combination with R1 parallel R2. Okay, so this is your total input resistance. You put in the values, you will find out total. Yes, it is in K. So this is for BJTs. Now last part of the slides is related to MOSFETs. Let's just quickly see what we have to find here. Again, I think we can do this in next session. So because these are 4 questions, so we can do it on one stretch, and these are just 4 questions on MOSFET only. BJT is completed for today. Or we can do MOSFET part in next session. Okay, we can end the session right now. Oh, do you have anything to say, Venkatesan? You can unmute yourself if you want to say anything, because I am about to end the session. Hello, am I audible? Okay, thank you very much. Okay, let me just put it here. Next session. Okay.